Welcome to Nanoindenter virtual training. In this video, we will cover some background information on the technique and some information about sample preparation. So how does this measurement work? We start with a tip or a cantilever that has a spherical bead attached to the end of it. With a Z piezo, we can control the motion of this entire assembly, moving it up and down. Now when we move it down, that bead is going to come in contact with the sample, and this long cantilever is going to bend. Now this portion here is an interferometer that can very accurately measure the position of this cantilever. And so as it bends, we can measure that change in its bending. And by doing this and knowing the stiffness of this cantilever, we can then extract the modulus or the stiffness of the sample. This image over here on the right is an image of the tips that we use. They are made out of glass, and the working portion of the tip is right here at the end, which is contacting the sample. This is a typical force curve. We are plotting the force applied by the tip versus the indentation of that tip into a sample. We approach the sample in this horizontal flat region of the curve, and at some point we make contact with the sample. This is where the curve starts to bend up. And we call then this portion where the tip is in contact with the sample the contact regime. We then pull the tip off of the sample in the retract portion, that's the red portion of the curve. And in this particular example, there is a very large adhesion between the tip and the sample. And so the tip is kind of stuck in the sample and releasing slowly bit by bit, and then finally it pops out or snaps out of contact before fully retracting. Typically, we are fitting the contact portion of the curve, and so the green line here is the fit to this data. Now most commonly we are using the Hertz model to fit that data, and this is the equation here that describes the Hertz model when we are using a spherical indenter as shown over here on the right. And I may take a minute just to explain this diagram. So this is our cantilever with this bead attached to it, and it is in contact and indenting into a sample. Now the dotted line up top here and this upper sphere represent the tip before it was in contact. So there is some distance z that the piezo moves, drives the tip, but the distance that we actually measure is this x. That's the kind of the bending of the tip. And we can then extract from that the delta, which is called the indentation. And it's the same delta that we see here. It's the distance that we've pushed into the sample with our tip or our bead. So if we come back to this equation now, let's define the parameters in the equation. E is our Young's modulus. That's what we're trying to extract from this experiment. V is the Poisson ratio. This usually has a value between 0.2 and 0.5. Very commonly for biological samples, we use a value that's close to 0.5. F is the force that we are measuring and extracting from this information. R is the radius of the tip, and delta again is our indentation. And so we can use this equation, or I should say the software uses this equation, to model our data and to extract a Young's modulus from that data. As you're thinking of getting started, you're going to want to know how to prepare your sample. In general, Petri dishes work really well. I've made measurements in Petri dishes that were 35 millimeters and larger. Typically, we are making measurements in some kind of solution, so we need some dish that has some sidewalls that can contain that solution, and that's why Petri dishes work so well. The sample must be fixed in place, however. We can't have any floating samples because as we try to press on them, they're just going to move. And so either the sample must be adhered to the bottom of the Petri dish or glued down to the bottom in some way. Another thing to consider is the thickness of your sample. If your sample is particularly thin, you might start to feel the substrate if you press too hard or too deep into the sample. So the general rule of thumb is that your sample should be 10 times thicker than the depth that you want to indent. That may affect you if you have relatively thin samples. In the next video, we're going to see how to load a tip into the instrument and also how to wet that tip.